In this video, we're going to look at vector equations of motion. So in AS2, we identified vector quantities such as displacement, velocity, acceleration, and force. These have magnitude and direction. So whenever we're looking at velocity, if we were thinking about vertical motion, then it's really important to identify whether up is positive or down is positive. Similarly, in direction, whenever we're going horizontally, we need to identify which side we're taking as positive for velocity. Whereas if we were to look at something like speed or distance, then that has only magnitude. It's got no direction, so it's a scalar. In situations involving constant velocity, we would use S equals Vt. So displacement equals velocity times time. What we can see is we're underlining the vectors and the scalars don't have it underlined. In situations involving constant acceleration, we can apply the constant acceleration formula as well. So we've got v equals u plus at. So again, the v, the u, and the a have all directions, whereas time doesn't, so they're all underlined and time isn't. S equals ut plus a half at squared, and we'll notice that the t, the half, and the t squared aren't underlined because they're not vectors. And s equals a half of u plus v times t, where we've got the u, the v, and the s. Now you'll notice we haven't got v squared equals u squared plus 2as. And that's because whenever we multiply a vector by itself, we get something slightly different. It's not quite as simple as that. So whenever we're thinking about vector equation of motions, we tend not to think about this one. When dealing with forces, then, we can also use this in vector form. And we can calculate the acceleration of a body using F equals ma, where forces we should be familiar with are all very direction related. Mass is just a quantity. The weight would act downwards, that would be a force. But mass is a quantity. Acceleration and force then are your vectors. So in our first example, we've got a car travelling with a constant velocity of 2i plus 3j. Find the displacement and hence find the distance the car would travel in 8 seconds. So what we've got is s equals vt. We know that the velocity is 2i plus 3j, and we're multiplying that by 8, and that's going to give us 16i plus 24j. So the displacement is 16i plus 24j meters. Now to work out the distance travelled, distance is the magnitude of the displacement. And we should remember magnitude, it's the size of it, and to work out the magnitude of a vector, we sum and square the coefficients of i and j, or the components. So that's going to be 16 squared plus 24 squared square rooted, which is the square root of 832, which is 28.84 meters to 2 decimal places. Next example, during a 20-second period, the velocity of a boat changes from 8i plus 12j to 6i minus 5j. What we've got then, if it changes from and to, this would be our initial velocity, and then 6i minus 5j is the final velocity. And 20 seconds is obviously the time, where I and j are perpendicular unit vectors. Assuming the acceleration of the boat is constant, find the acceleration of the boat. So if we think to our CVAT, we aren't worried about the displacement. The initial velocity we have, the final velocity we also have, the acceleration is what we're looking for, and the time we have. So the equations that we can use here will be v equals u plus at. Substituting in the known values, we get 6i minus 5j equals 8i plus 12j plus 20a. If we collect the i's and j's to one side, we'll have minus 2i minus 17j equals 20a. So then a dividing through by 20 is minus 2I minus 17J over 20 meters per squared second. Another example then, a box of mass 4 kilograms is in equilibrium. Now, if the forces are equilibrium, that means the resultant is equal to 0. Under the action of 3 forces P, Q and R, where P is 3, 5. Another way to write that, remember, is 3I plus 5J. Q is minus 2I plus 4J. Find R. So if the resultant force is 0, that means that P plus Q plus R must equal 0. So if we leave it all in column vector notation, that might be easier to do. We've got 3, 5 plus minus 2, 4 plus R equals 0. That's 1, 9 then, plus R equals 0. So R is going to equal minus 1, minus 9. Part B, if R is reversed, find acceleration given to the box. So if the value of R is reversed, what we're going to have is P plus Q minus R equals MA. So we get 3, 5 plus minus 2, 4 minus 1 minus 9 is going to be 4A. The left hand side simplifies to 218 equals 4A. So then A is going to equal 0.5 and 4.5 meters per squared second. Example, a particle P moves with constant velocity 12I plus 5J. Constant velocity, that means that the acceleration is 0. And it passes through a point A whose position vector is 4I plus 5J meters. So that's our displacement. Find the distance from the particle from O after 3 seconds. Well, if it's travelling with constant velocity, what we have is S equals Vt. So S is going to equal the velocity, so 12I plus 5J times T, so after 3 seconds, and that is 36I plus 15J. Now what this tells us is the displacement travelled in those 3 seconds. Now that's not telling us where it is, and that's telling us from time t equals 0 to t equals 3, it has travelled 36I and 15J. So what we know is initially it was at, so at t equals 0, the particle was at 4I plus 5J, and then in the next 3 seconds it moved 36I plus 15J. So it didn't move to that point, it went along that distance from 4I plus 5J. So that means at t equals 3, the position of it was 40I plus 20J. So we could think about that in a diagram to make it a bit clearer. So here's our origin. Initially, it's at 4I plus 5J. And during the 3 seconds, it travels 36I and 15J. So then the position here would then be 40I and 20J. So the position vector is 40I plus 20J. But what we were asked for was actually the distance. So to work out the distance, it's the magnitude of S, which is going to be the square root of 40 squared plus 20 squared, which is 44.7 meters to 3 significant figures. And just a few notes to finish. The first one, if a vector is parallel to I, then its component in J is 0. So thinking back, our I components are horizontal and our J components are vertical. So if we've got any vector which is parallel to I, then there's no vertical rise, so there's no J component. If one position vector is due east or west of another, then their J components are equal. So if we think about that in terms of a coordinate grid, so A and B are due east and west of each other, and if this was the I plane and the J plane, then to find their coordinates, they have the same J value. So the J components are equal. And if two vectors are parallel, then one is a scalar multiple of another. So parallel would mean that they have the same gradient, the same slope. So whatever this vector would be, if we have a parallel one, it must be the same gradient, which means then that in IJ notation, they would be all the same multiple of one another. And in AS2, we would have said that A equals lambda B, where A and B are the two parallel vectors and lambda is some scalar.